primary advantage of employing parallel conductors lies in the reduction of voltage drop across the wire's length. As conductor length increases, its ampacity, or current carrying capacity, tends to diminish. By implementing multiple conductors in parallel, the effective cross-sectional area of the conductor is enlarged, which subsequently reduces resistance. This reduction in resistance directly correlates to a decrease in voltage drop. The exceptions stipulated in NEC section 310.4 serve as safeguards to ensure the proper protection of these parallel conductors. Exception B mandates that each individual conductor possess sufficient ampacity to handle the complete load current shared among the parallel conductors. This stipulation is crucial because if one of the parallel conductors becomes disconnected, the remaining conductors must be capable of sustaining the entire load without experiencing overheating. Exception C focuses on the adequacy of overcurrent protection for each individual conductor. In the event of a disconnection in one of the parallel conductors, the overcurrent protection mechanism must activate promptly to prevent the remaining conductors from overheating and potentially causing a fire hazard. For parallel number 12 conductors, the overcurrent protection is capped at 25 amps. This limit aligns with the ampacity of a single number 12 conductor. Exceeding this limit would expose one or more of the parallel conductors to potential overload should one of the other conductors become disconnected. The rationale for using small parallel conductors, therefore, is to mitigate voltage drop while maintaining the necessary safeguards to protect the conductors from potential damage. To clarify, let us consider the principles of voltage drop, ampacity, and overcurrent protection more thoroughly. Voltage drop is the decrease in electrical potential along the path of a circuit. It's an important consideration in electrical design because excessive voltage drop can cause equipment to malfunction or operate inefficiently. Factors that affect voltage drop include the length of the conductor, the current flowing through it, and the conductor's resistance. Longer conductors, higher currents, and higher resistance all contribute to increased voltage drop. Using parallel conductors effectively reduces the resistance of the circuit, thereby minimizing voltage drop. Ampacity, as previously mentioned, is the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. The ampacity of a conductor is determined by several factors, including its size, material, insulation type, and the surrounding ambient temperature. NEC tables provide ampacity ratings for various types of conductors under different conditions. It's essential to select conductors with adequate ampacity to ensure safe and reliable operation of electrical systems. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors from overloads and short circuits. These devices interrupt the flow of current when it exceeds a predetermined level, preventing damage to the conductors and reducing the risk of fire. Overcurrent protection is a critical safety feature in electrical systems, and its proper application is governed by the NEC. When using parallel conductors, it's important to coordinate the overcurrent protection with the ampacity of the individual conductors to ensure that they are adequately protected. Now let's delve deeper into the specifics of NEC section 310.4 and its exceptions. This section addresses the requirements for conductors connected in parallel. The general rule is that conductors size 1/0 and larger can be run in parallel, provided that they meet certain conditions. These conditions are designed to ensure that the parallel conductors share the current equally and that they are adequately protected. However, the exceptions to this rule allow for smaller conductors to be run in parallel under certain circumstances. These exceptions are what we are discussing. Exception allows for the use of conductors smaller than 1/0 AWG to be run in parallel for specific applications, such as control wiring, provided that they meet the requirements of exceptions D and D. This exception recognizes that in certain control circuits the current requirements may be relatively low, and the use of smaller parallel conductors can be a cost-effective and practical solution. Exception B, as previously stated, requires that each individual conductor be capable of carrying the entire load current. This is a critical safety requirement because it ensures that the circuit will continue to function safely even if one of the parallel conductors becomes disconnected. To meet this requirement, the ampacity of each individual conductor must be equal to or greater than the total load current divided by the number of parallel conductors. For example, if a circuit has a total load current of 20 amps and uses 2 parallel conductors, each conductor must have an ampacity of at least 10 amps. Exception C requires that the overcurrent protection be sized such that the ampacity of each individual conductor will not be exceeded if one or more of the parallel conductors become inadvertently disconnected. This is another critical safety requirement that is designed to prevent overheating and potential fire hazards. To meet this requirement, the overcurrent protection device must be sized no larger than the ampacity of the smallest individual conductor in the parallel set. For example, if a circuit uses 2 parallel number 12 conductors, each with an ampacity of 20 amps, the overcurrent protection device must be sized no larger than 20 amps. It's important to note that the ampacity of a conductor may need to be derated based on the ambient temperature and the number of conductors in a raceway or cable. Derating factors are provided in the NEC tables. When using parallel conductors, it's essential to take these derating factors into account to ensure that the conductors are adequately protected. Now let's consider a practical example of how these rules apply. Suppose we have a control circuit that requires a current of 15 amps. We want to use parallel number 14 conductors to reduce voltage drop. Number 14 conductors have an ampacity of 15 amps. But we need to account for the fact that they will be installed in a raceway with other conductors. According to NEC table 310.15b3, if there are 4 to 6 current carrying conductors in a raceway, the ampacity of each conductor must be derated to 80% of its normal value. This means that the derated ampacity of our number 14 conductors is 15 amps times 0.8, which equals 12 amps. Since the derated ampacity of each conductor is less than half of the total load current of 15 amps, we will need to use at least 3 parallel conductors to meet the requirements of exception B. If we use 3 parallel number 14 conductors, the current in each conductor will be 15 amps divided by 3, which equals 5 amps. This is less than the derated ampacity of 12 amps, so we meet the requirements of exception B. To meet the requirements of exception C, we need to size the overcurrent protection device no larger than the derated ampacity of the number 14 conductors, which is 12 amps. We can use a 10 amp or 12 amp circuit breaker or fuse to provide overcurrent protection for the circuit. In summary, the exceptions to NEC section 310.4 allow for the use of smaller conductors in parallel under certain circumstances. These exceptions are designed to provide flexibility in the design of electrical systems while ensuring that the conductors are adequately protected. To use these exceptions safely and effectively, it's essential to understand the requirements of exceptions B and C and to take into account the ampacity derating factors provided in the NEC tables. It's also important to consult with a qualified electrical engineer or electrician to ensure that the design of your electrical system meets all applicable codes and standards. The application of parallel conductors, especially smaller gauges, is a nuanced topic that necessitates careful consideration of several factors beyond the basic code requirements. Firstly, the quality of connections becomes paramount. When dealing with smaller gauge wires, the risk of loose connections or improper terminations increases. These issues can lead to localized heating, arcing, and ultimately, circuit failure. Therefore, meticulous attention must be paid to the selection of appropriate connectors, the proper stripping of insulation, and the secure tightening of terminals. Regular inspection and maintenance of these connections are also crucial to ensure long-term reliability. Secondly, the physical routing and support of parallel conductors play a significant role in their performance and longevity. Smaller gauge wires are more susceptible to physical damage from bending, stretching, or abrasion. Therefore, it's essential to provide adequate support and protection along the entire length of the run. This may involve using cable trays, conduits, or other protective measures to prevent the wires from being exposed to physical stress or environmental hazards. Additionally, the routing of the conductors should be carefully planned to avoid sharp bends or tight spaces that could compromise their insulation or conductivity. Thirdly, the effects of electromagnetic interference, or ME, should be considered, especially in sensitive control circuits. Parallel conductors can act as antennas, picking up noise from nearby sources such as motors, transformers, or electronic equipment. This noise can then be injected into the control circuit, causing malfunctions or errors. To mitigate EMI, shielded cables or twisted pair wiring can be used. Shielding provides a barrier against electromagnetic radiation, while twisting the wires helps to cancel out common mode noise. Additionally, grounding techniques can be employed to minimize the effects of EMI. Fourthly, the impact of harmonics on parallel conductors should be assessed, particularly in circuits that supply nonlinear loads such as variable frequency drives, or VFDs, or electronic lighting ballasts. Harmonics are distorted waveforms that can cause increased current flow in the neutral conductor and overheating of transformers and other equipment. When using parallel conductors in circuits with significant harmonic content, it's important to ensure that the conductors are sized to handle the increased current load. Additionally, harmonic filters can be installed to reduce the levels of harmonics in the system. Fifthly, the coordination of overcurrent protection devices becomes even more critical when using parallel conductors. As mentioned earlier, the overcurrent protection device must be sized to protect the smallest conductor in the parallel set. However, it's also important to consider the time current characteristics of the overcurrent protection device. The device should be able to trip quickly enough to protect the conductors from overloads and short circuits, but it should also be able to ride through transient surges without nuisance tripping. This requires careful selection and coordination of the overcurrent protection devices to ensure optimal performance and protection. Sixthly, the documentation and labeling of parallel conductor installations are essential for future maintenance and troubleshooting. The wiring diagrams and panel schedules should clearly identify the parallel conductors and their associated circuits. Additionally, the conductors themselves should be labeled at each termination point to indicate their function and destination. This will help to prevent confusion and errors during maintenance or modifications to the electrical system. Seventhly, the use of appropriate tools and techniques is crucial for working with smaller gauge parallel conductors. Special wire strippers, crimpers, and torque wrenches should be used to ensure that the connections are properly made and tightened. Additionally, care should be taken to avoid damaging the insulation or conductors during installation. Proper training and experience are essential for working with these types of conductors. Eighthly, the long-term reliability and durability of parallel conductor installation should be considered. Factors such as corrosion, vibration, and temperature variations can affect the performance and lifespan of the conductors and connections. Therefore, it's important to select materials and components that are suitable for the environment in which they will be installed. Additionally, regular inspection and maintenance should be performed to identify and address any potential problems before they lead to failures. Ninthly, the cost-effectiveness of using parallel conductors should be evaluated in comparison to other options, such as using larger single conductors. While parallel conductors can offer advantages in terms of voltage drop and flexibility, they may also be more expensive to install and maintain. Therefore, a thorough cost-benefit analysis should be performed to determine the most appropriate solution for each application. Tenthly, the potential for future expansion or modification of the electrical system should be considered when designing a parallel conductor installation. If the system is likely to be expanded or modified in the future, it may be wise to install additional conductors or raceways to accommodate the increased load. This will help to avoid the need for costly and disruptive rewiring in the future. In addition to these considerations, it's also important to stay up to date on the latest codes and standards related to parallel conductors. The NEC is updated every 3 years, and it's essential to be aware of any changes that may affect the design or installation of electrical systems. Additionally, local codes and regulations may impose additional requirements that must be followed. By taking all of these factors into account, it's possible to design and install parallel conductor systems that are safe, reliable, and cost-effective. However, it's always advisable to consult with a qualified electrical engineer or electrician to ensure that the installation meets all applicable codes and standards.